But at least this lattice models, they're well defined. This makes perfect sense, right? And now once you take that and you say, well, is this actually the right model? Like, does this model show the behavior in the Ising model? Is there this point of non-analyticity, with temperature, or for percolation, that there's this critical probability? And what can you say about the probability that zero goes to infinity? There's some path. All of the work, I feel like the work of understanding that model and knowing that it actually applies to physics is the work of a mathematician. You really need that's a mathematical problem that requires mathematical tools, mostly analytical tools. And would you agree with me? Physicists, for a lot of the tools that they have, and they certainly know Taylor series and Fourier series and differential equations, and if they do GR, they know differential geometry. I feel like physicists don't do as much analysis.
Yeah, I think part of the reason for that is that analysis, especially, I think analysis, especially the analysis of PDEs, as it's practiced within mathematics, is it's a sort of soft subject. Not in the sense that mathematicians usually mean it, because mathematicians often talk to you about hard analysis versus soft analysis, and hard analysis involving a lot more estimates.
What is soft analysis?
Soft analysis would be functional analysis where you use tools that are not so much based on hard estimates and inequalities, but more on almost algebraic.
But
even hard analysis, the results that it gives are often very qualitative. So I know a lot of PDE people would they would bristle at this, because they'll say, no, I'm proving estimates and these C alpha norms and these Bessel norms or whatever. But if you have to explain to a physicist what it is that you're doing, the end result is, yes, you derived all these estimates, but what you're saying is this function is smooth. This type of, and maybe you can even measure its smoothness, this type of statement is typically not of interest to physicists. Statements about existence and uniqueness for physicists, unless they're really accompanied with very concrete, measurable quantities, are not of interest to physicists. So,
here's how here maybe is a simple example. Suppose a physicist, maybe even Newton, or I don't think it was Newton, but Fourier, he writes down an equation, the heat equation, which he calls the heat equation. The simplest equation he could write down to describe, heat based on some conservation principle, or you just take Newton's law of cooling and write it out in space and time. Okay. Here's this equation now. UT equals K Laplace U. Now, what does it mean to the physicist, as you say, that the physicist not interested in existence and uniqueness? But that's the whole thing. I mean, there's nothing, to my mind as a mathematician, you've written down an equation that we have very good reason to be interested in, but we're not certain, there's no certainty that this equation actually describes anything just yet. To my mind, what you have to do now is you take that equation, now that's a mathematical object, it deals with abstract mathematical things, and you have to answer, like, under what conditions will you have a function that solves that equation? And of course that deals with the problems of existence and uniqueness. And existence and uniqueness don't show up in a vacuum either, because depending on how what you mean by what constitutes a solution, the larger you take a space of functions in which you can consider what is the solution, the easier it is to prove existence, but the harder it is to prove uniqueness, and vice versa if you restrict so much. And so really what you end up doing with that equation, what it means to solve the equation and to prove existence and uniqueness of a certain type of function under particular kinds of conditions, is really that proving the regularity, is proving those estimates, all the hard stuff. How does the solution depend on the initial conditions, on the boundary, on whatever? And that somehow, when you can prove the right regularity theory for that equation, that's what answers that question of existence and uniqueness, and that something is smooth. And now you actually have solutions. Now you have something that you can go back to the world of physics and say, like, here's the observed behavior that comes from math. Here's what we can say about that there exists.
Yeah, I really disagree with this. I think you don't have to convince me that it's of interest, and that if your primary interest is in the mathematical structure of things, this is the route that you would go. But for a physicist, just knowing abstractly that something exists or that it's unique, this is of no importance. In most cases, when a physicist writes down an equation, the way that the meta story would be something like this. They would write down the equation, and the fact that the solution exists is almost self-evident, because they would say, well, this is physics.
Yeah, but I think that's the perspective I think is totally wrong.
The solution exists just because it is describing some natural phenomena. If the solution does not exist, then maybe we set it up the equation incorrectly. Maybe the problem is there. And I absolutely agree.
And that should really be a real concern.
There have been examples where mathematicians have been able to point out that there are non-existence results, or this equation doesn't quite make sense, or doesn't have uniqueness if you don't set it up correctly, and it's not so easy to set it up correctly. But these often come too late to be of any interest to physicists. And moreover, what physicists really are interested in is almost always fairly explicit solutions for which they can compute the long-term behavior, or at least in some approximation compute the long-term behavior. And that's what's of interest. That's why often analysis doesn't have that much especially analysis of PDEs, has often not had as much to contribute to physics, back to physics, as perhaps other fields. That's my impression.
I know that is the attitude of many people. I think this is a real point of disagreement here. I didn't know it was with you. I knew it was with physicists, because in my view, a lot of what you put forward as a model, you do not know at the outset that this is what really describes nature. It's really wrong to say, well, we know that there is a temperature, so there must be solutions to the heat equation. Wait. You just wrote down this heat equation, making a lot of assumptions so that you could write down, and you did the right thing because you wrote down the very simplest model that took into account the kinds of things, the kinds of forces that you thought were at play. Of course, there will be all sorts of other forces. You ignore all kinds of other things, and probably it's very smart to do so, because an equation that took into account all these other things will be a lot harder to solve, a lot harder to figure out what's going on. So you start by taking the simplest thing that you think has a chance of describing the behavior at the level you want to look at it. But then the question of whether that model actually does what it is that you hope that it does becomes a mathematical question, in my view. It's no longer something you can't say, well, of course there's a temperature, and of course it doesn't blow up. Maybe of course it doesn't become, you start an oven and the sides of the oven are held at a certain temperature. That you shouldn't have 5 seconds in a temperature spike that's way higher than any place where you're heating it. Right, but that's a feature that you can see when you solve that equation. That comes out mathematically of that abstract model that you tried to write down, and it is the solving of that equation, in my view, that tells you in the end that was the right way to talk about heat.
So I guess we're not. It's not so much a disagreement. I'm just describing the situation, the cultural situation, and I think these cultural differences are, as very often, they're justified to some extent by the facts. There aren't that many examples that we can point to where mathematicians analyzed some equations and went back to the physicists and told them, look, we did all this work, we got all the estimates, and what you did, what you guessed was really wrong. They exist. I don't want to pretend that there are no examples, but these examples are extremely rare, and more often than not, in those situations, the obvious response that physicists can come back to are one of, well, there are many possibilities, but two of them are very common. The first is that what you're pointing out is an instance where the model clearly does not work. It doesn't work because we didn't take into account friction, for example. It doesn't work because we didn't take into account that, at some point there are like finite size effects, and you cannot really do a continuum approximation. Now you can go back and say, well, okay, this is sort of rewriting history. Now you're telling me that actually you knew that this model could not have worked. But that's a sociological response. It's not a response on the math. And then number two, I think a related objection that they often come up with is that even if you can give examples where things clearly don't work, these examples are examples that are artificial, that don't actually occur in real life. So they will tell you, okay, yes, for this equation describing, for example, water or the movement of waves, you can find solutions that blow up, but that's because your initial data to start with was not something that we ever see in real life, or because the way you set up the equation. I think I would be the problem with I understand. I agree that if there were infinite time, and if everybody had time, for example, to deeply, study partial differential equations, they would realize the value of what sort of insight it can give you. But if you're a physicist and you're mostly interested in describing nature, and you look back historically at what happened, you don't have many examples where physicists were wrong because of a delta missing there and epsilon missing there, but because they did not have a hard bound in any norm. I agree that the problem is that if you actually want to study, if you go back, if you as one person, not as a part of the body of, as somebody trying to advance the body of human knowledge and just trying to do research, but if you as one person, you try to sit down and construct for yourself a completely logically coherent version of physics, including all these equations, and then you probably need to learn a lot of the math, and you probably need to know, for example, that these equations that you're writing down make sense. All I'm saying is that in practice, when you go to a physicist and you say, I have proved in 1,000 pages that the solutions exist for some time that is possibly incredibly small compared to any sort of timescale that you're interested in, they're not going to be impressed by this.
What is really of interest to a physicist? And what is the difference between the way a physicist looks at a differential equation that describes some phenomena and a mathematician? Because a mathematician maybe is interested in things like existence, uniqueness, and behavior of solutions, right? The way that you're describing. And these questions make a lot of sense to me, as what you'd ask, given a model, given an equation, or given some variational principle, something that you can attack. These are the natural questions, it seems to me, to ask. I haven't yet talked to any physicists, so I don't.
I think you should ask. I would guess, well, a physicist is interested in first writing down the equation, writing down the model, and B, deriving, let's say, a reasonably rich family of exact solutions to this equation, which capture real life phenomena or help us make predictions.
Right. These are things. Right. Phil also brought this up. Yes, these are things you'd like to do. First, to write down a good equation that you hope has some chance of explaining what it is that you're looking at, and also you have some chance of analyzing it.
Right.
and this process of giving good exact solutions or models for solutions in some cases. It helps you to see what put some barriers, some sense of what's going on with what's happening there, for sure. So what is it?
I can give an example. So I think there's like an example where I think mathematicians and physicists would give very different answers.
Okay.
To this question, or a good space to work with this question would be the Navier-Stokes equations, which describe water flow or fluid flow, how some incompressible fluid moves in time.
Okay.
And
we'll just
So let's just stir a cup of water.
Okay, so the whole column of water, the whole cylinder is initially circulating, as you say. Okay.
Circulating around. You have some olive oil or water or whatever it is that's moving around. And there's some equations or system of equations really that describes or is supposed to describe this motion, Navier-Stokes equations. And what the mathematicians hopes to do is to establish mathematically, if you look at these equations, that solutions exist and are nice and smooth for all future times.
So you don't get the kind of phenomena that you were talking about with the curvature blowing up and the soap films coming apart. You shouldn't have that happen, with real water. So you hope that your equation that describes this thing doesn't actually have solutions that seem to do that. Is that what you're saying?
That's exactly right. So something that a mathematician might hope to prove is precisely this, that solutions never develop these weird behaviors of something blowing up at a finite time. And this question the answer is unknown.
Right.
And mathematicians
$1
regard
million
this as,
problems, right?
Yeah, as a very central problem. Well, for a couple of reasons. One, I think it's just interesting whether singularities could form or not. The other one is actually it would help you answer the uniqueness question. So provided the solutions to this problem remain nice and smooth, you could say that there is a unique solution as you move forward in time. But if mathematically something like the blowing up of curvature happened at, after 10 seconds or something like this, then the question of uniqueness becomes delicate. And as you move forward in time after that point, there might be two different ways mathematically to move the solution forward in time. And it's not clear. In fact, these days, there's pretty strong evidence for non-uniqueness.
Oh, really?
Yeah.
Non-uniqueness. So you can. What would that mean?
So this is a very mathematical thing. What people have studied is they've studied the situation where the initial data are singular. So they're assuming that the velocity is nice and smooth, except it gets very, very, very large and infinite even at one point. And they ask, let's solve this equation forward in time and say, is there a unique way of doing this or not?
And for which they have to have some generalized sense of solution that allows them to start with something which is right. Okay.
So there's some physical notion of solution, or what people really think this is the correct notion because of energy conservation, things like this. And people have fairly strong numerical evidence that there's non-uniqueness of solutions to this problem.
It's numerical. How does that work? They ran it twice and it came out differently. What is?
Yeah, I don't want to get too much into it, but what's the way to say it? So people can, I think, write down one solution to this problem. If the initial data are particularly symmetric, then there's like an explicit solution that one can write that I guess keeps the symmetries forwards in time. It's called a self-similar solution. And now what people do is they say, how stable is this self-similar solution? in the sense that if I perturbed that initial data a tiny, tiny bit, then as I solve forward in time, does the solution look like the exact self-similar solution or not? Or does it wildly deviate? And I think what people have discovered is the so-called instability, that tiny perturbations in the initial data could possibly give rise to wild deviations later on. And that corresponds to, say, the analysis of the eigenvalues of the spectrum of some operator. So when I say numerically, I think they mean that they managed to make numerically some estimates of eigenvalues of a certain differential operator and show that one of them was had a positive real part.
Okay, that's technical. That makes sense. That makes helps me to understand. Of course, I really I've never touched Navier-Stokes. I guess the maybe it's not exactly relevant, but I'll just bring you in on the kind of thing that I was discussing with Phil. The attitude that I want to argue against is the one that says, of course, we're not interested in you mathematicians proving such a thing as existence or uniqueness, because of course there's a solution, because we know there's a temperature. We know the water does something. So what are you doing? Trying to prove? It's like you're trying to prove that the water exists. What does that mean?
Yeah, I think that if you asked a physicist, about all these issues we've been discussing with Navier-Stokes, he might be exactly what you're saying. What are you talking about? It's I don't see the point of
really, but you were describing was so much more clearly precise. It started going to that, like you can see from instability some issue with uniqueness, or that you're interested in this specific nature of, say, singularities, because it will be manifest in the behavior, say, right before. I guess my attitude is of course you have to do the math. My attitude is you don't really know. You're not like really allowed to claim totally that, of course, you know that this applies because we have a physical thing. Of course, it follows this equation. You don't really know that thing follows that equation until you have solved that equation mathematically and know enough about the behavior of solutions to say that it is a good predictive model for what you actually see. And then it's something that now that we know that this is a pretty good model and exhibits this behavior under these conditions where the model is good.
Yeah, I would agree with you as a mathematician. I think this is very important. But also, I mean, I think my attitude is also partly that I'm inherently interested. I don't know. I'm curious. I have to find out if these things happen.
Yes, I think this is
like problem solving.
Right. This is definitely a part of my training. Like although I learned, the thinking by which people derived or proposed some of these equations in the first place. So at least historically, if I go back, I can tell someone why what's the equation of a hanging cable, or why we say this is the wave equation for a vibrating string, and now look what we can do with that equation. That's not what I do on a daily basis. I take the equation someone already wrote down, and I'm like, well, what can I say about it?
Right.
What's true? Right, there are all these interesting questions you can ask about the solution that's actually sometimes very difficult to get at.